We have ICESat2 team. All right, we're the ICESat2 team. We were collaborating between InSAR folks and ICESat2 folks, trying to improve measurement using SAR by integrating the two data sets. So our motivations for doing this project grew out of conversations between people who use InSAR data and people who use ICESat2 data. And our goal was to see if we could combine spaceborne LiDAR and InSAR instruments to estimate snow water storage. We wanted to see how maybe in the future we could combine future ICESat satellites and the future NISAR instrument. And we also wanted to learn more about the two instruments and work together and learn things from each other.
All right, so we have a couple of specific questions. First one is there's a question of phase constraint that I didn't get a lot into in my presentation, but is a challenge, especially in areas where we don't have in situ snow depth data. So the first question was, can we use this to improve our ability to constrain that phase when we're doing snow water estimation using InSAR? And then the other piece was, can we use this to validate? So if we have NISAR up there, is ICESat2 a technique we could use to validate and improve our abilities to use this technique? When we were getting into that, we were then thinking about coherence of radar satellites and how that's going to compare to ICESat2. So we did some analysis of that. And then just a general feasibility of what's the scalability of comparing these two very different instruments, or kind of the specific questions.
Okay, very quick some background on ICESat2. ICESat2 carries Atlas, which is a photon counting satellite LiDAR. The beam is split into 3 main tracks, each with a weak and strong beam, and that is providing elevation tracks. The ground tracks repeat every 91 days, but you can't rely on that in the mid-latitudes, so you might get repeating type tracks, you might not. And we mainly worked with 3 different products, the ATLO3, which is the photon cloud, ATLO6, which provides 40-meter windows with 50% overlap, and then ATLO8, which is a 100-meter block, but provides more photon classification. And combining this with slide rule, we have a lot more of control over the data, and we can kind of customize how we're getting our ICESat2 elevations, which is really helpful. And then from this source called Open Altimetry, these are just showing an example of some ICESat2 tracks, so you have a bit of an idea of what those look like. The orange line is showing the ATLO6 elevations calculated from the photon cloud and the ATLO8.
Yeah, I'll go super quick on this because hopefully you all remember the tutorial, but UAV-SAR is an L-band airborne synthetic aperture radar, and interferograms derived from UAV-SAR. Phase shift of those interferograms can be used to estimate snow depth change between the 2 time points. And in order to actually get that phase difference, it's a relative thing. So in order to actually like tie it to like a real difference, you need a reference point. Typically, seems like the UAV-SAR snow team has been using SNOWTEL sites for the reference point, but one of the ideas here was that if you have a UAV-SAR or a ICESat2 point where the 2 beams cross, that's kind of like contemporaneous with the UAV-SAR acquisitions, that maybe you could use that difference, that known difference, as a kind of reference point also. So we'll get more into that.
Yeah, so we made some maps here of taking the UAV-SAR shape files from the 13 sites that we've seen and just trying to understand how many tracks and passes are you going to get from ICESat, because it is an instrument that's meant for the poles. It's a little more sporadic and random. You're dealing with cloud cover. So in each of these maps, this is constrained from December 1st to April 30th of this year and last year, the 2022 water year, or 2021. This is a mistake. But how many passes are you getting through there? And we see the most, which are sort of these horizontal shape files like Loman or also the Montana one, you get higher amounts, 10 passes per year. And if we're going towards this for NISAR, NISAR is going to have a massive swath. These are about 16 kilometers. NISARs will be hundreds of kilometers. So we're going to be getting a lot of ICESat2 data over this area that made us be like, okay, this is feasible. We should keep moving forward with this project. Next here, you again.
Me again. So the other part of the feasibility kind of element is not only looking at the spatial overlap of these two sensors, but also the temporal overlap. So this is just a kind of a plot that shows that for Grand Mesa. These vertical blue bars are ICESat2 passes over Grand Mesa, and the horizontal red bars are UAV-SAR pairs over Grand Mesa. So you can see that there are some overlaps between the UAV-SAR and the ICESat2. In particular, in 2020, you can see that there's these kind of two ICESat2 passes that actually line up pretty well with these sort of three interferograms. So yeah, that's sort of the temporal feasibility piece.
And I will quickly go over how we retrieve the snow depth by using ICESat2 data. So here, the concept is very simple. So in the left side, you can see the ASO snow-free DTM, and we just subtract this DTM from the ICESat2 snow on elevation, which you can see in the right side. So by using this technique, we just calculate the snow depth on the ground mesa area. So in this plot, you can see these points are the snow depth measurement from ICESat2. And here background, you can see we also display the snow depth measurement from snow tail sites. So basically, there are two snow tail sites around the ground mesa area. One is Mesa Lakes and Park Reservoir. So if you see this plot, you can see ICESat2 snow depth measurement agrees pretty well with the snow tail measurement. But you can see there are some large variations in ICESat2 measurement, and which is because of the spatial offset between ICESat2 and the ASO DTM. And in addition to this content, we also look at if ICESat2 can really detect the snow accumulation by comparing two different days. And very fortunately, we can find two tracks. One is from December 2019, and another is from April 2020, and they are only 70 meters apart, which is very, very close. So we just compare the snow depth for these two tracts. So I don't know if you know, but ICESat2 has 6 beams, and we just compare these 2 beams among that 6 multiple beams. And here in this table, you can see ICESat2 snow measurement is kind of overestimate compared to the snow tail measurement sites. So if you see the snow accumulation between these 2 dates from ICESat2, you can see the difference is about twice than the snow measurement difference from snow tail site. So yeah, and we will compare ICESat2 with UAV-SAR.
Yeah, so here we compare ICESat2 snow depth with UAV-SAR snow depth. So keep in mind that the snow depth that we derive from UAV-SAR is the change in snow depth. So to make this comparison work, we accumulated the change in snow depth using the ASO snow depth for February 12th. As shown in the previous slide, the temporal overlap occurred in February 11 and March 11. So this is the result for the February 11 ISAT2 snow depth and UAVSAR snow depth, and this is for the March 11 UAVSAR and ISAT2 snow depth. We see that the scatter plot does not really agree well. ISAT2 has high variation from -2 to 4, and as Young mentioned, this is due to the offset in ISAT2 overlap. And we can see the median actually really agree well. And another thing that we did, as mentioned by Zach, is that we corrected for the phase change using ISAT2 snow depth. And when we compare that for UAVSAR snow depth derived from uncorrected phase change, and with UAVSAR snow depth derived from corrected phase change, we see there is an improvement in the result of UAVSAR snow depth, given that showing that ISAT2 might give a promising result to improve UAVSAR snow depth.
Yeah, so going forward, we're really interested in when we combine these two sensor technologies, how well they complement each other and whether or not they are constrained in their performance by similar topography and snow condition types. So just doing a quick comparison here between the photon confidence that we get from ISAT2 and then the UAVSAR coherence, which is a big factor in determining whether or not we can use those crossover points to back out a phase change from the UAVSAR images. So I think Zach and others will explain further.
All right, so yeah, another big part of this, as Mia was mentioning, is trying to figure out where, like how the ISAT2 confidence compares to UAVSAR coherence. And so we basically tried to answer that question by extracting all the ISAT2 points, or extracting all the coherence points that were covered by an ISAT2 point. So sorting it by confidence, you can see that actually where UAVSAR coherence is higher correlates with areas where ISAT2 confidence is lower. So the satellites kind of, they kind of go in opposite. And here on the right, you can see kind of just a map comparing that to I believe, slope. That would, I don't know, that one wasn't too informative. So then we made some additional figures kind of tying in slope versus UAVSAR coherence, and we binned it by each plot will be a different confidence level of ISAT2 data. And so we compared slope and elevation both to UAVSAR coherence. And for these, I'm not sure. I think we need to do some future analysis to see if there's anything here, but preliminarily it looks like there definitely is some sort of a relationship that could be teased apart if we had more time.
All right, this is a little bit out of order. This should go before what Naheem talked about. So one of our goals was to try and use ISAT2 crossover data as a point that you could then adjust your phase shift to so that you get higher quality InSAR data. So we wanted to find ISAT2 tracks from dates that coincided with UAVSAR pairs. And where ISAT2 from those two dates overlapped. That is pretty rare. And we got really lucky and actually had a crossover within our site. So on the left, that's the polygon delineating the outline of where UAVSAR was flown at Grand Mesa. The blue tracks there are an ISAT2 tracks from March 11th, 2020. And the orange is from February 12th, 2020. And those, we have UAVSAR flights basically on those exact same days. So super lucky. When we zoom in on those ISAT2 tracks, we see we have two crossover points. So we found the snow depth difference at these 2 points based on ISAT2 data. and used those points to constrain the phase shift in the InSAR images. That's like impossible for you to see. On the upper left, we have the phase changes without any corrections, so no tie-in point. On the upper right, we used a SnowTel tie-in point. So that is like the standard way that people process InSAR data. On the bottom left, we have the InSAR data with a single tie-in point using one of the ICESat2 crossovers, and the bottom right is the other ICESat2 point, uses the tie-in point. So basically using the ICESat2 crossovers, on the bottom left, you can see when we adjusted the phase shift, we ended up accumulating far too much snow on the order of 1 meter compared to about 20 centimeters in the uncorrected version. When we use a second ICESat2 point, we had a much smaller shift, and we're much closer to actual snow depths we're seeing at snow pits. We haven't actually done a spatial comparison of snow depths for these two yet, but that is the next step, and it could happen pretty quickly. But basically, the takeaway here is that ICESat2 can be used to adjust your phase change, but there are still some constraints to ICESat2 data, and so the more points of crossovers you have, the better. So we need to make ICESat3 for snow depth. It needs to follow NISAR around.
Yeah, this was a very fun project. It was definitely a big scope. I think it was kind of a lot to take on. A lot of days of just figuring out what the two sensors look like and how to get the data. But I think we had some cool takeaways. It was fun to see how we can use these two sensors to complement each other, and how they're going to work together. And I think ICESat3 will absolutely need to follow NISAR right along the same track. So we have a strong satellite proposal there. Yeah, it was a really fun time. So thank you for your time.
Any questions before? So you mentioned that it was pretty rare to have the ICESat2 crossover. Look at any of the other sites. Anywhere else. This was not that happened.
I was just going to say we could take it back to the spatial plot that Jack made of the ICESat2 crossovers over the where we have InSAR data. And I think the timing is a key component. I mean, here you see we have different dates, but they don't necessarily line up with UAV SAR flights. We didn't really look into the timing of that. I think the takeaway here is that if that all lines up, this kind of analysis is possible. And for the future, when NISAR is flying, we have a much wider range of possible dates and locations where we might get those ICESat2 overlaps at the right time and space.
Yeah, I think UAV SAR is too limited, but sorry. Once we have NISAR every 12 days, I think the chances of having these overlaps is going to be a lot higher. So I think it's going to be something that could be much more useful.
But if NISAR keeps getting delayed, we might not have any temporal overlap of ICESat2 and NISAR. So we need to get NISAR up, and we might need a ICESat3 for this to work.
Any first thoughts on influences of terrain? How this might influence your angles, steeper, less steeper, shallower snow, deeper snow?
Right. So I think for ICESat2, we get better agreement with other measurements flat areas, and deeper snow is better in general because you just have more of a signal. And I know we talked a bit about the drawbacks of UAV SAR over terrain. So I think Grand Mesa, like we said, is probably the key, like the best place for this to happen. And we just would need more data and need to look at the other sites to see if it's possible over slopes with more varying terrain. But I'm sure that varying terrain will make it more challenging.
No more questions. We'll take a 15-minute break, so we'll come back.